Howdy and welcome back. Let's go ahead and revisit our sequence of nodes from a previous lesson. We said that we could create this type called node, which could store some data such as an integer value, as well as having a pointer to an object of the same type, a node. So here we can see that data is going to be one field within a node object storing essentially the data at that we're interested in, similar to how an element in an array would store some sort of value. And then the next field is going to store a pointer to the next node within our sequence. We can go ahead and create a single node on the free store by writing new node and assuming there's a parameterized constructor, which will take an integer value to initialize data with, as well as initializing next with the null pointer. We could see here that in a node at some address, so here's the address, would be returned if we requested a new node with the initial value of data of 7 on the free store. Notice here that null pointer is going to be represented by the integer value of 0. Since the new operator returns an address, we need to store that address somewhere. In this case, we're going to store it in head, which will serve as the gateway into a sequence of nodes. It is storing the address of this first node within a sequence. So that address gets stored into head, and the aesthetically pleasing drawing over here on the right shows essentially what's set up here. We can see the various fields of our node object highlighted as they are in the UML diagram. The data field shown in purple, storing the integer value of 7. The next pointer pointing to nothing as symbolized by the arrow going to the orange square with the next throw. As we were introducing this topic, we said we could come up with a procedure to essentially, beginning at the head node, walk through the linked list until we arrive at the last node in order to go ahead and tag on an additional node to increase the sequence size by 1. Up here in the at the top, we have the initial sequence of nodes that we'd like to go ahead and add, say, an additional node into that sequence at the end, storing the integer value of 8. How would we go about this? Well, what we're going to need to do is come up with some sort of pointer into this sequence of nodes that we can move from node to node until we arrive at the node whose next pointer is pointing to nothing. We set that up as cur node here and go ahead and initialize it to head. We will emphasize why it is important to set up a node pointer to perform this traversal towards the end of the lesson today when we introduce traversing a singly linked list. But anyhow, once we have this, what we can go ahead and say essentially is if current node is pointing to something, that is, we're not dealing with the empty list condition. And remember in the previous lesson, I mentioned that this little algorithm snippet here is not considering an empty list. If you'd like to do so, you can implement that behavior on your own. So we're assuming before we hit this that there is essentially at least going to be here one item in the list, excuse me. So if so, we're going to get into a while statement, which is going to perform the traversal. So right now we have this set up as cur node pointing to head. And while cur node's next, in this case, cur node's next is pointing to a node. So this is going to evaluate to true. We'll get into the body of the loop and move cur node forward. Excuse me, I should be doing this up here. Because that other diagram is showing the result. So in the case that we're pointing to something, which we are, we go ahead and move cur node over. And that's what saying cur node is equal to cur node's next is doing. Now at this point, the conditional is going to evaluate to true, or excuse me, to false. The reason being is we finally arrived at the node whose next pointer is pointing to the null pointer. So here we're at the perfect point to go ahead and tack on that new node. And we can do so by assigning that cur node's next a new node with the integer value of 8. And then point that new node's next pointer to the null pointer. So there we go. There's a simple traversal. And as we were building this up in the previous lesson, we said there's actually perhaps a better way to go about this, where we wouldn't have to actually traverse through the linked list, or excuse me, through the sequence of nodes each time in order to arrive at the tail or the last node within that sequence. However, we did mention that this would take a little bit of extra accounting because it would leave us with an additional node that we'd have to node pointer that we would have to consider in each of our operations to this sequence to ensure that head's always pointing to the correct location. And then if we introduce this idea of a tail pointer, that it is always pointing to the last element within our sequence. So if that were the case and we had this and we were interested in adding to the end of the list, the operation becomes as simple as allocating memory for a new node. In this case, maybe we'd like to tag on one with 9, and then simply setting tails next to the address of that new node. So again, let me just draw this out. We stored that address in temp, and now we're essentially putting that address into tails next. So if we had that node out there, when we assign it the address, we can see that the last node in the sequence, the current tail, is now going to point to 9, whose last pointer is pointing to the null pointer. That relationship is now disrupted upon the assignment. And then the last thing for us to do is go ahead and point tail to the new tail. This is where that additional accounting comes in because we have to ensure that tail is always pointing to the last node in our sequence and head always to the first. Now we talked about the destruction process here briefly, and I just want to provide a brief recap thereof. We said that if we wanted to deallocate memory for the sequence of nodes residing on the free store, we're going to have an equal number essentially of calls to delete as we initially did to new. We said that simply writing delete head is problematic because that's going to essentially cause a memory leak. We would have wiped out the node that served as our gateway into this list, leaving all of this over here, minus the kind of last one because of that tail pointer, inaccessible. So that would be a huge memory leak with the size and magnitude dependent on the size of your list, or sorry, of your sequence of nodes. Instead, we came up with an algorithm that we'd go ahead and employ if we wanted to clear out this sequence of nodes from the free store, essentially returning their memory so that we could use that, so the free store manager could use it for something else. We said that in order to do this, we need to traverse the list and call delete on each node's address one by one. To do this, the procedure we came up with was to make use of the head pointer along with a node pointer next initialized to the null pointer. And then the procedure begins while we haven't reached the end of the list. We can assign next the value of heads next to preserve that. So notice here that the first time through, by assigning next the value stored within heads next, we have a gateway into the remaining portion of the list. Therefore, when we call delete on head, all of this is not lost. We can still access all of this through the next pointer. And to kind of keep with the consistency of this, we go ahead and move next, or excuse me, head over to point to what next is pointing to, and then we'd go ahead and move next over to the adjacent node, or I guess not adjacent, to the next node within the sequence, because again, they're residing wherever in memory, and the only thing linking them together is their addresses. They're not contiguous like an array. And we complete this process until heads at the null pointer, which in that case would communicate to us that we have successfully visited each node and we have called or invoked the delete operator on each of the node in the sequence's address. So again, this process will continue until the last node where the assignment of next will be the null pointer, prompting the value of head to become null pointer after the last element is deleted. And we mentioned that how this might look algorithmically would be while head, and then we'd have something like node pointer next equals heads next, delete head, head, equals next, and just continue that process. Okay, so we've revisited our sequence of nodes, and now we're ready to encapsulate this sequence within a class. We'll call it singly linked list, and we'll go ahead and encapsulate the behaviors that we can apply to that data within that class.